Hello all, let us see a simple circuit which provides reverse polarity protection for a 25 volt input with a load current capacity of 5 amps. So for this reverse polarity protection, there are two methods. While design engineers can come up with more methods, two predominantly used methods. One method is to use a Schottky diode where it doesn't allow any reverse polarity to be used, and then there is another method using a MOSFET, specifically P-channel MOSFET. So here we are talking about P-channel MOSFET. So the main difference between using a Schottky method and a P-channel method is that basically for a Schottky diode, if the load current increases beyond a certain limit, there will be lot of power that will be dissipated across the diode, and you might have to use lot of copper underneath or use a heatsink to pull out the current. There is another method, as we said, which is a MOSFET based, which can carry higher currents. Power MOSFETs can be used for higher currents and design the circuit easily. So most design engineers, if they are having a smaller load currents, they go for Schottky diode. If the load currents go beyond 4 amps, 5 amps, 6 amps kind of requirement, P-channel MOSFET is the preferred one. So let us see here how to design a simple P-channel MOSFET based reverse polarity protection for a 25 volt 5 amp load current. So if you see here, this is the MOSFET which is selected, and the MOSFET has a VTS of 30 volts. So in reality, as our operating voltage is 25 volts, the VDS should be around 40 volts, so that any spikes and all doesn't damage the MOSFET. So here, for just the simulation purpose and show a circuit, we have used VDS of 30 volts, and then this particular MOSFET which we selected has a VGS of VGS threshold of -2 volts, and you should not give gate to source beyond 10 volts. If you give beyond -10 volts, it the MOSFET breaks down. So -2 to -10 volts is in between what the VGS should be, and then the drain source resistance of this particular MOSFET we selected is 3.6 millivolt. So for this particular MOSFET, if you see, so for a given 5 amps of current, the power dissipation across this MOSFET is given by I square R, which is I is nothing but 5 amps, 5 into 5 into 25 into R. R is 3.6 milliohms, because once the MOSFET is on, this is treated as a simple resistor. Okay, so the entire dissipation we have to calculate is based on the drain to source resistance, because that is where the entire current will flow. So once you do this, you see that 90 milliwatt of the power would be dissipated across this, and the theta j we have considered 24.17 degrees centigrade per watt. So you can check the data sheet, the theta j, and if you are operating your MOSFET at 85 degrees centigrade, so the power now to explain you example, if we are using a MOSFET or a system in which we are using this solution is operated at an ambient of 85 degrees maximum, okay, or the operating temperature, we should say operating temperature of 85 degrees, then we have to calculate the temperature rise of every component at that temperature to know if the operating temperature of the specific components used is going beyond their specifications or not. So here the M1 MOSFET which we have considered has an operating temperature of up to 150 degrees centigrade. Now we have considered 85 degrees as the ambient. So 85 plus power dissipated is 90 milliwatt, and then theta j, this is the resistance. So R into I, in electrical terms, in thermal terms, it is theta jc, and then theta ja, sorry, the junction to ambient, and then the power, which gives 87.1, which means if you use this MOSFET at a load current of 5 amps, the temperature rise of that particular MOSFET for a operating temperature of 85 doesn't go beyond 87.1, which means very good actually, because we have a very good limit. This is because the theta j and then the kind of current that we are allowing it to pass through. Now that is the MOSFET selection. So MOSFET selection is based on VGS, VDS, low RDS, as much low RDS as possible, and then at a given operating temperature, the temperature rise of this component should not exceed the operating temperature of the MOSFET. So that is how first MOSFET will be selected, and then we have to drive this gate, right, of the MOSFET. So this gate drive should not go beyond 10 volts. So for that we have used a simple GNR based circuit at the output of the MOSFET, which is the source, and this breakdown is selected as 18 volts. So why we have selected 18 volts GNR diode here is, so once we give 25 volts here, what happens is immediately, because of the inner diode, body diode, there will be 25 volts that will be seen here at the source, and slowly when 25 volts is seen here, this gate starts charging after 25 volts is seen there, and slowly this potential will increase. So this potential shall be increased, should be increased such that the diode, the gate voltage should not go beyond minus 10 volts. So now if you see here, this is 18 volts, and here if you give 25 volts, 25 minus 18, which is nothing but minus 7 volts is the potential here. Okay, so you can increase it to 20 volts as well, so that you will have potential of 5 volts. You can reduce to 16 volts so that it goes to 9 volts. It should not go beyond 10 volts. So that's how the GNR diode will be selected. And then once the GNR diode is selected, you should select a resistor such that once GNR turns on, there should be a current limiting that should be done. So here we are doing current limiting such that the power dissipated across the GNR diode should not increase beyond its specification, which is 200 milliwatt. So once the current is flowing through this, the voltage is 18 volts. So I is, if you consider P is equal to V into I, so I is equal to 200 milliwatt by V, which is nothing but 18 volts. That means current should not go beyond 11 milliamps. If it goes beyond 11 milliamps, the power dissipated across the GNR increases beyond 200 milliwatt and it might burn. Okay, so current is limited that way. So once we calculated the current for a power dissipation of this GNR, we have to calculate the resistor. So we know 25 minus 18, 7 is the voltage here, and then if you use R is equal to V by I, V is nothing but 7, I is nothing but 11 milliamps, which gives 636 ohms. So why resistor only here is, once this GNR starts conducting and this potential starts increasing, so the entire current will flow through this resistor only, because we know MOSFET has a very high impedance. So we have to limit the GNR diode current to ground only. Okay, so that is why this resistor is very critical. Any wrong resistor calculation would lead to failure of the GNR diode. So we have used 5 ohms here to just provide a 5 amps of current. so 5 into 5 will be 25, uh, so 25 volt here. So the I is equal to V by R, which is nothing but 5 amps will be the current. So this is how a simple P channel MOSFET reverse polarity protection circuit is designed. So one is MOSFET selection, second one is Zener diode voltage and current calculation, and third thing is resistor calculation. So if you see the circuit, example, let us probe the, we are simulating here. If you probe the voltage here, you can see it is 25 volts, and then if you see the current through this, it is 5 amps at a maximum. And then if you see the current through here, this is coming around 11 milliamps, because the voltage, the current is 5 amps here, so it is showing very less. And then if you probe the voltage here, you can see the blue line, which is 7 volts. Okay, so the circuit with this 25 volts is functional. Now let us do a simple scenario. We are going to delete this and have another voltage source which is connected in reverse. Okay, 25 volt. And then once we try to simulate, you can see here there is a 0 volt at the output. If you calculate the current, it is in picoamps, so that means there is no flow. So if you connect a reverse 25 volt, the diode is not allowing the current to pass through. Okay, so this is how the